We have no choice but to dig into turbines, and yes, there are several types of steam turbines. Steam turbine or turbine is a rotary mechanical device used to drive rotating equipment, such as a generator, by extracting thermal energy from pressurized steam. The amount of heat energy in the steam determines the amount of work performed. The greater the heat energy in the steam, the greater the amount of work that can be performed by the steam turbine. Steam turbines have fewer moving parts, requiring less maintenance, and are more efficient than reciprocating steam engines. Common uses of steam turbines include generating electricity and driving auxiliaries such as pumps, fans, and compressors. A steam turbine can consist of several stages, each having a set of revolving blades. The size of the blades increase with each stage. Steam turbines require dry, superheated steam, and many types of loads need only moderately superheated steam. Okay? Now we get into these different turbine types. Non-condensing steam turbines. A non-condensing steam turbine is a steam turbine that exhausts at atmospheric pressure or above. Non-condensing steam turbines are normally used in steam plants that require low amounts of low pressure process or heating steam, and if the exhaust steam were not used and allowed to go to waste in the atmosphere, the steam turbine would have a very low thermal efficiency and will waste a considerable amount of energy. The exhaust steam from small non-condensing steam turbines is sometimes used to heat feed water in an open feed water heater. Non-condensing steam turbines must use a large amount of the available exhaust steam to maintain maximum efficiency. In addition, non-condensing steam turbines do not have condensate returns. Condensing steam turbines. A condensing steam turbine is a steam turbine that allows condensate to be reclaimed for use in the system. The condensate is returned with some heat still in it, and the heat is then reclaimed at an open feed water heater. The condensing steam turbine are commonly used on medium to large units and operate with an exhaust pressure of 26 inches Hg to 29 inches Hg vacuum. The higher the vacuum is, the greater the efficiency is. This low exhaust pressure allows the steam to expand to a greater volume and release more heat to perform more work. Plant conditions determine the steam turbine best suited for an operation, and plants that are designed for maximum efficiency may use both condensing and non-condensing steam turbines. Steam from boilers is used to drive steam turbines. Steam turbines drive a shaft that turns within a generator to produce electricity. Step-up transformers are used to increase the voltage to the level required for transmission in the lines. Impulse steam turbines. Impulse steam turbines use steam velocity as a force acting in a forward direction on a blade mounted on a wheel. Impulse steam turbines may contain many sets of revolving blades that are divided into stages, and to produce the force, a nozzle is located before each stage. The steam velocity increases and pressure decreases as steam flows through the nozzle. The nozzle directs the steam to the turbine's revolving blades, and on the first stage wheel, this causes the shaft to rotate. Steam is then routed through fixed blades, which redirected the flow of steam to another set of revolving blades on the same wheel as the first stage, and the steam then enters the second stage nozzle, gaining velocity before striking this revolving blade of the second stage wheel. Steam exits through the exhaust opening, and the steam exits through the exhaust opening. The pressure drop incurred in an impulse blade turbine is through the nozzle and not the blade. The fixed blades are used to redirect the flow of steam between each set of revolving blades without any change in pressure or velocity. Steam enters the first stage nozzle and drops slightly in pressure as it passes through, but the steam velocity increases. The steam strikes the revolving blades, imparting energy to the blades but losing velocity in the process, and then the steam then enters the fixed blades and changes direction without losing pressure or velocity. Once again, the steam strikes a second set of revolving blades with the corresponding drop in velocity but not in pressure, and then the steam velocity returns to its initial value after passing through the blades before the next stage to increase the velocity. The steam passes through the second stage nozzle, and the velocity-pressure relationship is then repeated as the steam passes through the second stage revolving blade again. The pressure drops through the first stage and second stage nozzles before being exhausted after the second stage. Wow. The diameter of the wheels increase in size from the first stage to subsequent stages to allow for the drop in pressure and an increase in volume. Most steam turbines are designed to have a steam velocity that is twice as great as the blade velocity. That is a lot to wrap your head around. The velocity of a turbine blade is directly proportional to the velocity of steam flowing past the blade. In other words, turbine blades turn faster when the steam velocity is higher. In an extreme case, the steam energy could be extracted by one set of blades. However, if the steam pressure drop is very high, the steam velocity will also be very high, and this causes the blade and shaft to rotate very fast. This can cause vibration that can damage the turbine, which makes sense. Therefore, the turbine uses velocity compounding to reduce the speed of the blades. Velocity compounding is a method in which the energy from the steam is extracted using multiple stages in a turbine to reduce the steam velocity and pressure in a short amount of time. This was the longest 7 minutes of my life, and there's like 2 more types of turbines, and my nose hairs, I guess, need trimming because they're itching. Do we really want to get into reaction steam turbines? Newton's law states that every action there is an equal and opposite reaction. Reaction steam turbines operate on the principle for part of this action. Instead of nozzles, a reaction steam turbine uses fixed blades for its first stage. Fixed blades are designed so that each blade pair acts as a nozzle. Steam expands between each blade pair, and the expanding steam gains velocity in the same manner as the impulse nozzle. This steam, which is high velocity, enters the blades of the moving element, imparting a direct impulse to it. Steam is then directed into the nozzle-shaped blade passages. The steam expands into the nozzle-shaped passages and gain additional velocity. When leaving steam turbine blades at a higher velocity, a backward kick or reaction is applied to the blades. This is where the term reaction steam turbine comes from. Impulse reaction steam turbines work primarily at a higher speed, resulting from larger drops in pressure. They are smaller and weigh and cost less than reaction steam turbines of the same capacity. Reaction steam turbines are primarily low-pressure steam turbines because of the loss around the blades at high pressure. Reaction steam turbines have small drops in pressure per stage, resulting in small amounts of steam expansion with low output of work per stage. Many stages must be used to obtain the full range of pressure drops throughout the steam turbine. Impulse reaction steam turbines combine impulses and reaction blading. Usually there are several stages of impulse blading in the high pressure end of the steam turbine, with large pressure drops through the nozzle. The reaction blading in the low pressure and causes small pressure drops each row of blades. In addition, the impulse reaction steam turbines are commonly run on high vacuum for even greater efficiency. In some impulse reaction steam turbines, nozzles are used. In others, the fixed reaction blade acts as a series of nozzles directing steam against the impulse blades. The same parts are required in an impulse reaction steam turbine as those in a separate steam turbine. The governor steam admission to The governor controls steam admission to the first stage. The overspeed and low oil pressure trip shuts off steam to the steam turbines if necessary. Superheated steam is usually used for driving steam turbines to prevent moisture droplets from entering the turbine. Moisture in a steam turbine can erode the turbine motor. And that is 10 minutes. Thank you for joining me for impulse reaction steam turbines, condensing steam turbines, impulse steam turbines, non-condensing steam turbines, and steam turbine types. Like, subscribe, share, and feel free to donate to my Ethereum or Bitcoin address if you want to support this content creation. Please have a positive and productive day, and this is for artistic and educational purposes only. I hope you find it valuable. I sure do.